Okay, so this comes out of question number 5. So we have this cubic, and I've drawn this cubic over here. So it looks like it's a nicely symmetrical cubic. Let G be the function of the tangent at x equals A. Let B be the x-intercept of the tangent. 3 marks for a show that question. Golly. So tan line of f of x at x equals A gives me interactive advanced, no, calculation line, tan line at A. Simplify the answer, so that gives me y equals 3a squared minus 1x minus 2a cubed. And when y equals 0, x equals solve for x equals 2a cubed on 3a squared minus 1. Since b is x-intercept, therefore b equals 2a cubed on 3a squared minus 1. Done. 3 marks. Golly. Now that must be pretty important information, that the x-intercept of the tangent is equal to that. It's a show that question. It must be used somewhere else in the questions. Okay, part B. State the values of A for which B does not exist. B won't exist when 3a squared minus 1 equals 0, because you'll have a division by 0. So a squared equals 1/3, a equals plus or minus root 3 on 3. State the nature of the graph when B does not exist. When B does not exist, there is no x-intercept. Therefore, it must be the tangents that go through there and go through there. Therefore, the nature of G of A, it's a horizontal linear line. State all the values of A for which B equals 1.1. Okay, so this is my x-intercept. My x-intercept equaling 1.1. And I'm going to solve for A. Four decimal places. Thank goodness for that. So A equals negative 0.505, 4 decimal places, 5052. 0.8084. And is there another one over there? There is 1.3468. The graph of f of x has an x-intercept at 1 and 0. State the value of A for which B goes between those two values. So B goes from 1 to 1.1, and B equals this. So what I'd like to do is I'd like to graph this. So I'm going to go keyboard, math3 given A equals x. So then that replaces x's into the expression. So now I can edit, clear all, okay, graph this. And I've got to go between 1 there's the line of 1 and 1.1. There's the line of 1.1. Golly. So I've got some values of x between these two, remembering that 1.1 is the green and I can equal the green. So analysis, G-solve, intersection, the green one, and the curve. So I'll accept the curve and the green one. And I get negative 0.0505. So negative 0.05, negative 0.505. Three decimal places. That's that answer there. There must be 1.1. Ah, of course. And the other one over here is 8.8. Okay, so that's those. So I know those. So I'm interested in where does it equal 1. So analysis, G-solve, intersection, where it equals the red one. Okay, that one, and the red one is that one, and I get an answer of, I picked the wrong one. Do this again, analysis, G-solve, intersection between the curve. So negative 0.5, so to negative 0.5. So A goes from, it can equal that one, but not equal that one, union. And if I jump over here, it's equal to 1 there. So in actual fact, I don't have to worry about that because it's always going to be between 1 and 1.1 between the other ones. So 0.808, A going to 1.347 are the values of A that give B between 1 and 1.1. Over the page. Okay, what have I got? I've now got two tangents, and the tangent at B and the tangent at the x-intercept of B. Now this thing here, the x-intercept of the tangents, this. So this is where this show that. We've been waiting a very long time to use this, but there it is, 2a cubed 3 minus a squared minus 1. So I know that b equals 2a cubed on top of 3a squared minus 1. Okay, so how am I going to use that? Find the values of a for which g and b exist are going to be 3x squared minus 1. So the derivative of b is 3b squared minus 1. And that's going to equal the derivative at a, which is 3a squared minus 1, and I know that b equals this. So I'm going to have 3, that's better. So a equals negative 1, but that's the problem is that b would equal negative 1, a equals a and b would equal a. So it's going to be these answers here, which are plus or minus root 5 on 5. And they're the only two occasions when this will happen. Over the page, golly, oh no, down the bottom of the previous page. They're showing us that these are odd functions. So the feature of the reflecting over the y-axis gives you the same as taking the original reflecting over the x-axis. So p of minus x would equal minus x cubed plus w times minus x, which is minus x cubed minus wx, which is negative p of x, therefore shown. Now, they did that so that I knew they were odd functions. So if you reflect it over the x and y axis, you get the same thing. Okay, the property of the graphs of this. Find the values of w such that the tangents of the graph that have the same x-intercept, x-intercept, x-intercept. Bingo, bingo, bingo. I'm going to use this knowledge again. and I find out the tan line, at t, and I simplify that, and I then find that the x-intercept of that, so make that answer equals 0, solve for x. Then that gives me an expression for the x-intercept, and that expression for the x-intercept is 2t cubed on top of 3t squared plus w, and if that equals minus t, I then solve for w. And it's going to equal minus t because we are saying that the tangents at those 2 points are going to be parallel and they'll have the same x-intercepts. So advance solve for w. And I get w equals minus 5t. So w equals minus 5t squared is going to be the values of w in terms of t. And lastly, state any restriction on the values of m, n, h, and k given the image of p under the transformation so that the tangents occur, so that we have this nice little pattern occurring where the tangent here and the tangent here have this x-intercept which is the same value as that tangent. And because we have these symmetries occurring, if I have a k value going up or down, the k is a vertical translation, and if I move these up, these patterns will still exist. If I reflect them over the x-axis or the y-axis, the patterns will still exist. If I stretch and stretch, the patterns will still exist. So m, n, and k can be anything. But what I can't have is a translation sideways. So h has to equal 0 is the only restriction we have on m, n, h, and k if you want this nice little pattern of tangents that are parallel, one tangent cutting the other at an x-intercept which is equal to where the other tangent attached.